implemented by it, but basically many of you already have defined your variables, or you use the input files provided by others, like the tutorial tools. Some of you have not used it at all, so I can give a brief overview how you start from the very basics, how you write a variable, how you select the outcomes, and things like that. If you already done that, it's already pretty basic, so you could just now listen to me and go ahead with doing one of the tutorials for the day. And I don't know if you have any suggestions for which ones are on. Let me see.
Okay. So can you put the on a little bit up?
Okay. This is so for today. There's well, the first link is not really a tutorial. Is well, there's something that looks like a tutorial, but actually doesn't have output files. It has input files though that you can use, and I'm going to show them. There's three others. One to do metadynamics. As I said, Jave from Zan's group has provided this. Basically translated to NAMD the iron dipeptide tutorial from Group, and the protein ligand standard bioimages from Krishibo, and the ABF tutorial. And the others are gonna, for tomorrow, are gonna be relevant after you take the third. But I think the first one for tomorrow, methods for calculating potential mean force, is also the one by JC and his student Anthony. That's also quite relevant to what I talked about. So you may want to do one of those and start ahead. If you are not familiar enough with what these tutorials ask about, then I can show you how to get started. So the website that it's linked here, well, actually also here, is this one. And there's examples here. So there's an examples repository, which is this one, which you can download. Here's, I'm logged in, so it asks me to clone or download, but for you it's just probably going to be downloaded. But anyway, you can download the zip file for everything. And it's called examples-master. Master just means the master branch because it's GitHub is the method to maintain source code, but basically just you just use it in the master branch as well. Okay. So let me open the zip file. You're not recording this, are you?
I know. You want me to stop?
Yeah. Okay. So start everything. And then I can open the shell. Okay. The README file, it says here that you can, this is where basically most of the files are. There's also additional data sets. Those are relevant for the, I mean, these are forms, very helpful. The additional data sets are available. But basically, there's two examples. One is 2 helical peptides, and it's a slightly larger system. The other one is 2 small molecules, tetramethylammonium and acetone. It's a very tiny system. You can get a PMF in a matter of seconds. So I'm going to go there so you can look at it briefly. So you can go to the TMA ACO folder. And there's several folders here. The README file again explains what it is. But what I want to do now is do something which you may do at home, but just to get you started, which is go and start to write a configuration file, and then basically you want to start from scratch without having writer's block. For NAMD, well, this should also be covered at some point, but the NAMD configuration file is much bigger and complex, so we take a long. Folvas is a smaller asynchronous code, and it will be much simpler. So I open this folder test and I edit the file test.nmd. That's the script for running NAMD. So you notice that to make it simpler, I put everything that is NAMD parameters for NAMD in the script here, which is common/common NAMD. So you can check there what all the input parameters are. And the name of the output files is going to be prefixed by the prefix of the script. So you can also change name test to test2, and all the files are going to be named test2 in the output. Which is convenient because then you can look at the files. So this is where you set the number of steps, and then this is where you load the NMD parameters. This is where you run. We'll call the NMD parameters are hidden here, and since all of you have been using NAMD already, you should be familiar with what's in here. If not, then you have to learn machine learning. But basically, I can run NAMD on this one just fine. And it runs pretty quickly, 100,000 steps. And you get basically several files. And there's no PSF file here, it's in the common folder, but you can load it like this. These are the molecules into the licorice. You do diffuse around a bit, so even in the relatively short time, it's a gas phase system, so they move around. Okay, so this is a NAMD simulation which is running. Able to run standard measurement analysis. If you want to do an unsampling or free energy, start from an input for a simulation that can run stable on its own. If your simulation, NAMD simulation blows up at this stage, I don't want to hear about it. You need to add more things on top afterwards. But after having done check that this input runs, then we can add more configuration to it. I'm going to show you one very simple configuration, which is to run a stirred molecular dynamics to separate these two molecules and to actually compute the free energy for the work doing that. If you have other requests, I can show them later, but this is, I think, the most general example that I can do. So let me edit the input file again. And then where it says add stuff here, that's where I'm going to put something. So if you want to use any of the methods that I talked about and others that I've not talked about because they have time, but you have a backend. Colas is one of the components to use that. You will need other components for it too, for the string method, for example. You will need the TCL scripts that additionally distances, but then this is what you need to start with. So basically, you need to learn to use Colas. Because otherwise, to speed up calculations, it doesn't turn it on, and it doesn't do the extra work that's needed. Although I believe that if you don't request any atoms, it just doesn't do anything. If you don't. So this keyword is almost superfluous at this point. And now, once it's turned on, well, remember that in most installations nowadays, nearly all of them, NAMD runs a configuration file, which is also a TCL script. So you can run TCL commands. Most of them are going to be executed after all the parameters for the force field have been loaded, but then you can control what the simulation does. So before running, you want to define the additional input, the additional biases that you want to add. So if you want to know, for example, you want to add configuration for Corvus. So there's a command CV, which is the interface for Corvus, and then you can basically have subcommands like config, which reads a configuration string. And I don't know if I have the time, it's worth it doing later, but this command is also available in VMD. So everything I'm doing here for NAMD, I can also do it interactively in VMD. I can maybe do it later for something more. So if you want to test a configuration and you don't have the input file ready for NAMD because you want to generate a full PSF, etc. But you have a simple structure in VMD, protein, that you haven't solvated yet. You can just use the definition in VMD, test that it works, and after you develop it, you can also do the same thing for now. So you can move from one to the other. Now, the configuration is a string. In this case, you can also read an external file. In this case, let me put a string here so that it's in line with the NAMD file. So you can either you do the file for callbacks from outside or like put it in here. I'm going to put it in here for clarity. Once you have more stuff, of course, it's always better to load an external file. Otherwise, if the main NAMD file becomes too long. So I'm going to put quotes, and I'm going to put something in between. You're going to have to define a variable for the collective variable first. You're going to have to define the distance between the two molecules. And then you want to define the protocol that you're going to do on this distance. So first, let's define the collective variable, the distance. And then we're going to define the protocol of that. So distance, you do it by allocating, by defining a callbar braces block. Forget about discovering that it doesn't mean anything. It's just syntax highlighting that the email thinks it's important. So basically, this is now a string. For all selecting purposes, TCL treats this as a string argument, which you can pass between one comment and another. So here you pass it to the CB config comment, and then inside you will turn on the callbacks module and make it read the string. Inside the string, you can put also variables. So you can put, for example, it's not important here, but you can say, I think the stretch coordinates file, it's possible to use. I'm going to maybe show them in another example. But let's say that, I'm going to show it later, you want to use number of steps or any variable, you can put it in here. But let's first define the variable. So I'm going to give a name to this variable. The name distance is a good, this is a good name. And then we're going to define the function that this variable is going to be. So it's going to be a distance function. So I'm going to type distance. And again, because I'm going to put more lines of input, again, I put braces in there. And now, distance, you will, of course, look up the manual, but all the examples you have the same, very simple distance function, so you know that. Now we're going to put the two groups of atoms, and the distance is going to be between the centers of mass of these two groups. So we have to put group 1 and group 2. Now I'm going to put just braces for now, and then fill them in a bit. But it's a good idea to put the braces first, because a lot of the definition callbacks is nested. NAMD, of course, runs the entire system with the same input, so you have one-liners all the time. Variables can be a bit more complex, so you have many nested braces. Put the mentioned braces first, so you know you're not missing it. Now, how to put the selection here? This is a graph. Yeah. Question? Yeah.
Is distance a keyword?
For
we just defined it right now.
No, distance is a keyword here. Exactly. So the syntax is quite similar to NAMD's, except that it allows multi-line input. So the syntax is name, so name of the keyword. So the keyword name is a recognized keyword, and this is the name that you put. This is also good. Then distance is a keyword. You could actually give a name to this object too, because if you have this collective variable that is a function of many pieces, you can give names to these pieces. You don't have to, but you can. Then how to select the atoms. So this is where I'm getting ready to express my gripe, which is the gripe of many other people. It's like, why can't we have VMD atom selections in NAMD? Maybe one day that they will come. For the time being, there are some keywords that are very limited for callers, and then there's options to do roll and other some files. One option is that we can just number the atoms. We can look at the system, which is small here, and we can take the atoms all together. So let me save this file for now, and I'm going to look at what the atoms are. So I'm looking at the PSF file. This is the PSF file for the system. There are two molecules. One is the tetramethylammonium, which is called NC4. It has the first 17 atoms. There's carbons and hydrogens. You can include all of them for the time being because it's a tiny molecule. And then there's the other one, which is acetone, is the atoms 18 through 27. So naturally we can make two groups, one molecule, the other molecule. And we can select the atoms by numbers, if we know these numbers. There's other options. If you have a protein sequence, for example, you can select atoms by name and residues range. So if you want to select all the C alphas in a certain interval, there's a keyword for that. You can just select all the atoms named C alpha in this range of residues. You can also select the PSF segment names, etc. There's other options for that too, but let's do one, see it work, and then maybe worry about the other options. So let's remember here. First molecule is atoms 1 through 17. Second molecule is, of course, 18 through 27. Okay. So now I'm going to add the keyword. It's going to say, give me the atoms within this range. And the keyword is, as a very unexpected name. But I want to highlight something here. Here, the first atom is 1. You will pick the numbers of atoms from the PDB or the PSF. And the first atom in the system is 1. In other cases, you may deal with situations where the first atom in the system is 0. If you get a VMD selection and you tell VMD for that atom selection to return the index of the selection, you can do that. This is one way of copying the VMD selection from VMD to NAMD. And there, yes, you can practice. But the VMD, by default, return, if you say get index starts from 0. If you want to convert the VMD selection into one for NAMD, I think also TSC Forces. No, TSC Forces uses 0 based. And I would like to use numbers that match the PSF or the PDB.
You can use also get 0.
Exactly. Yeah, I was going to say exactly. If you want to get the numbers in this form, like with the first atom being number 1, you tell atom selector get 0, and those are the numbers you're going to use. You can get the whole, you can list them one by one. In this case, the keyword will be atom numbers, but arrange is more complex in this case. Save, always. And the second molecule was 18 through 27. Now this is done. We have created the variable. It's going to be computed. Not much else is going to happen to it unless we tell NAMD to do it. But since it takes nothing, let's do a test run and see how that happens. It runs again. I think now it should be, yes. There should be other outputs. So besides the ones from NAMD, coordinates, velocities, BCD trajectories, all that stuff, you have the ones that is the same prefixes from the NAMD files, but with dot callers, to distinguish. I mean, they come from the same simulation, but they have different contents and they're grouped together so you know what part of the code coming from. I may argue that more parts of NAMD could be organized this way so that you could have modules for different things. I think maybe for the chemical, we're going to get there at one point. Anyway, there's different things here. This is corpus.state. This is a state file which can be used to restart the simulation. You don't always have to do that with the corrective variables, but if you have metadynamics or ADF, you're carrying over the history of a simulation. So you're going to use that in addition to the coordinates velocities. So we've seen it in examples. This is a backup file, which you don't care, unless we corrupted our last result. This is a trajectory file of the corrective variables. So now, since these variables are few numbers, we don't need to be too stingy with the space. So it's actually not a binary file like the DCD, it's text file. And we can look at it. And it's highlighted like this. You can have the first column is step number. This is the same step number that NAMD uses. But if you continue simulation and you load in the state file for Corvus, you will continue over indefinitely. It can become larger and larger, even if NAMD every new job starts from 0. Because you have to do that. You have to be able to carry over simulation. If you use a first time step in NAMD, then first time step is going to be used. So by default, Corvus will default to carry over its own time step. But if the user for NAMD does something which very few people do, which is to write first time step, then we will honor that. There was an issue came up with Grace Main a couple of days ago. But most of the time, this is not an issue. You just the point is that this is a text file that the first column is going to continue when you do different jobs that are consecutive, which is nice because then you can concatenate into a single plot. The second column is the value of the distance, and then it's written with as many digital precisions as possible. NAMD spends a lot of time to do calculations in double precision, unlike other codes, and we should definitely use that. I think in that space you can also use single precision, but with membrane systems, you won't. Okay, now this is just printing the variable over time. Fine, I can do it in VMD. I can load the trajectory and calculate this number for myself. You can plot the label, you can add the bond and plot the label over time. It's easy to do that. Let's do some enhanced sampling. So go back to the input file, and now I can add more stuff here, which is now I'm going to define a bias here for that's going to move the simulation from one point to another. It's going to do external work on that. So we're going to define a harmonic restraint, which is going to move. So we're going to do steer them. Simple. You could put it again. This is a single configuration part of Corvus into this string, or actually in another string. However you do it, it's good. I generally like to do different pieces of configuration separately, because then if you want to turn off something, you simply can comment out that part, just like you comment out single lines of the NAMD. And now we turn on harmonic potential. And let me close brace and quotes, because of course I will always forget. And now I'm going to define the restraints. And I don't, contrary to the variable, you don't have to give a name. I mean, you always have to give the name to the variable because you're going to use it at some point. For the bias, for the restraint, you don't have to give a name. But if you have many restraints, giving a name makes it easier to identify. So we're going to name this harmonic bias harmonic. And then this is again just specifying the name, just internal bookkeeping. Now we're going to tell that this harmonic restraint is going to be applied to this variable. So the potential will be applied to the variable dummy. This harmonic potential, which I don't have to write except that such like this. It's right like this. It's a scaled harmonic potential, which by default is the simple one in this case, because this is a width that we are assumed here, and the width here by default is 1, so you don't have to worry about it. So basically, this turns out to be this way. Okay. But keep in mind that if you're changing if you're putting a custom width here, which is not 1, then this is going to appear in the potential. This is documented, and also the tutorials is discussed practically. But at this stage, this is the harmonic potential, not the 1/2 not. That could be important, and not tremendously so if we're going to move it right away. And so now I have to write the center of the restraint, at least the center of the first step. We have to start with the R0 being chosen by us. So let's put like 4 angstroms. Sorry, address centers.
Will be better too.
So the initial center of the restraint will be 4. Now you can see here that the curvers and centers is plural. You can apply this harmonic potential to multiple variables at once. Of course, they're going to be added together, but it means that the same potential can be controlled simultaneously. So if you had like, hypothetically, let's say that you had like the Ramachandran plots, the Ramachandran angles, you define phi of psi, you call those variables phi and psi, you just write phi, psi, and then you put the center here, and then whatever angle you like. So just put, if you don't want to do multi-dimensional stuff, you just add more variables here. So, what? You're first.
Hold on. What does the centers represent in the equation?
R0.
R0.
That was my question. Okay. I was going to get to that. Okay. So R is dummy. You know what? You can keep dummy if you prefer. It's just me. So R0 for R is going to be 4. If you have another distance, you can define another value if you have other R's. But we have just one here. And now the last thing is that we have to specify is K, the force constant. Yes?
So for the center command, can I specify the value as the initial distance in the initial file instead of explicitly?
So no, you could theoretically, but it's going to be it's not going to be a round number for sure, and also this may be carried out, especially the way now that we're doing inputs with NAMD scripted. With the NAMD being fully scripted flow, you could be loading input after the fact. So you could be actually defining this at one point and reading the NAMD input later. So for example, think about using coordinates from the VMD file, but then use bin coordinates, which you've used before to restart the simulation. Suppose you load, I'm not 100% sure which you could ask Jim or David, but suppose you define coordinates first. Then you define the collective variable here, and you do like you say, read the initial coordinate. So we'll take it from the PDB file. But then you load in a bin coordinate file, which is going to override the coordinates, that's going to change it there. So the safest is to say it explicitly. Everything else, yeah, you can be read as we go. But we don't know at this point what data has NAMD read or not. So the safest is to assume that it could also be read after. So let's be explicit here.
And you can always use VMD to prepare all these call bars, so you can pre-compute the distance in VMD and then use directly
Yeah,
here.
there are some calculable variables that are not easily to compute
Yes.
beforehand.
Yeah.
No, but you can, okay, maybe in a little bit I'm going to do it for VMD too, so you can actually compute that and get the number, they're just going to paste here. So, force constants. Now, let me put, say, 5 kcal per mole per angstrom square, but this is 5 kcal per mole, and then the part of the potential specified here, the other part is if you put the width here. But as I said, if the width is 1, this is 5 kcal per mole per angstrom square. But we are aware that this is clearly stated energy, and the other part of the potential will be defined by the width if you have one.
So the width is the distance, in this case, 1 angstrom.
Yeah, I mean, I can, so the default is 1, but I can write it explicitly. Okay? So what does width represent? For any bias or algorithm that uses a grid in corrective variable space to write a PMF, ABF, metadynamics, they're both going to do that. So you can define the spacing using this way. And this is the one keyword that basically gives you the unit of the variable. Suppose you're using a distance here, which has a range in effective, has a range likely between 4 and 10 angstroms. And then another variable is a dihedral, which has an interval of plus or minus 180. It has a very different range. Use that width to identify a unit of amplitude of spacing in the space of the corrective variable. And then the harmonic potential is going to be applied the same way to each one of them. But this rescaling allows you to basically not have to do the math of the force constant for each one of them, because you can say always when R minus R0 is this much, then the energy is going to be 1/2 K.
So, but if the value of the width is higher, it won't sample. There might be a problem with sampling. You want the width to be very close to each other, right?
So it depends what you use the width for. In this case, it's not even required, so you can put it initially. If you want to use ABF or metadynamics, you want a PABF at the end, you want a grid, so the spacing of that grid is going to be width. And really, of course, if you have a very fine grid, it will require more time to sample, but it's of course more high resolution.
So why shouldn't the width be a part of the harmonic definition? Why is width a part of the coal-fired definition?
You could do that, but the point is that you could define harmonic, and then ABF, and then another harmonic, and they're all going to use the same width, so you end up repeating yourself. So you could actually do that in some cases. You could redefine that. Maybe this can be extended to all of them. But in any case, the convenient thing is just setting one CF for the variable, because then when you write the variable, you know what you're doing there. You know that that's specific to that variable.
So take that way, shouldn't the center also be there?
Maybe, but really, this is the point where you're deciding what is the bias that you're doing there. And I think the center of a restraint should go with the restraint. Width here is basically mostly telling us the unit. So this is in the unit of angstrom, so the unit width is 1. Mm-hmm. If you're using different units, you're going to use a different width. Okay. That's what the meaning is. But really, the center of the restraint, I think, should go with the restraint. But the point here is that as much information as possible is put with the variable. What's the advantage of that? Is that I can keep the variable and the examples in this same repository follow that convention. I can keep the same input for the variable and change the part that does the VMD method. So you can do still NAMD, ABF, metadynamics, just by changing this part. Okay, first constant, I forgot them all. And then, okay, this is defining a fixed harmonic restraint. I could test it out, but I mean, we know what it's going to do. It's going to narrow. Let's do the more interesting stuff. Let's do the biasing over time. So I want to move the distance from 4 to 12. So I set target centers to 12. You know, I have the habit of putting .0 because for computers sometimes it probably is not a problem here, but this is just to say there is a real number. It's not an integer. That's the reason why I put in .0. But
this is important for any TCL script to do. If you're using TCL and if you want to do divisions or ratios, use .0 if you are.
If you mean a real number, yeah, it will. Okay, and then so with all NAMD, well, core was more specifically, to move this restraint from 4 to 12, how quickly, we can tell how many steps this should take. And the nice thing is that this number of steps can even be longer than the time step of one simulation, one short job. It can be carried over in multiple jobs. So you can do a slow steer in this simulation that carried over beyond the work time of the computer. But in this case, I don't have that kind of time. And I'm going to set a short number of steps. Now, how many here you can do? Okay? So if you remember this NAMD input, I set a variable num steps 100,000. And then that's what I use here. Suppose that I want to maybe do this in 50,000 steps, but like half of the total. I want to do the first TLMD for the first half, and then just let the restraint fix for the rest of the time. So I can set a lower number. And now, like, see what I'm doing here. This is a string here, and I'm using a TCL variable in it. Corval itself will not understand TCL, but this is a string that is managed by NAMD at the TCL level. So the variable num steps is going to be set to 100,000, and then this string is going to be passed to Corvus, and then it's going to be executed there. And the same goes with the bracket expansion of TCL. If I want to divide that number by 2, this is the integer division, because I'm just doing an even. I want the result to be an integer also, so I don't need to do the .0 here. So this is basically saying, take the number of simulation steps that are requested, and that was the variable num steps. And take half of that. This is how quickly I'm going to move the harmonic restraint. I'm making up an example here, but just to show you that you can do this kind of things. You can really embed the syntax into your NAMD input and control everything with variables so that you can automate things. Yeah.
So the variable target centers,
Mm-hmm.
does it mean that R0 goes to 12 slowly or R goes to 12?
R0 is from
Exactly. So then what is the range of R?
we'll do the simulation. We see whether the force is sufficient to keep it close or not. We can look at the trajectory afterwards. Okay, and this defines already the bias, the student bias. Now, of course, we want to do something useful, so what we can do is we can track it over time. So, yeah, we can look at R And we can also look at R0, and we can plot them both. So this will write to the colvars.traj file the centers of the restraint, but this is one of them, is R0. So R0 is a function of time, is going to be written in one of the columns of this file. So we can plot it. Another thing that is interesting, we can write the work performed. This is the work performed along R0. So it will be 0 at the start. I recently corrected a small inaccuracy. There wasn't a big deal, but you may want to use a recent version. So you know that at step 0, the work is exactly 0. It doesn't start from something that is placed from scratch. And so basically, it's going to integrate between 4 and 12 how much force is applied, and then this force is going to give us the work. And then this work we can actually try to interpret as the free energy using the VMD technique, which is just integrating work. And this is it. Now, let's hope, yeah?
Can I see that right now?
Yeah. The bottom?
Can you also output the force at each time step?
Output what?
The force, the harmonic force at each time step.
Sure.
All right. So okay.
Isn't it supposed to be constant?
What the applied?
The force.
Isn't it supposed to be constant?
No, because it depends on R minus R0.
Oh, yeah.
R0 is changing over time, and R definitely changes over time.
I have a question.
Yeah.
So when you say the centers and the target center, if I have a periodic system,
Great question. So distances are computed using the minimum image convention. So if you make it bigger than half the box, it's not going to get there. I mean, R0 can go wherever you want because the number you set, R is never going to go there. It really, with very boundary conditions, I'm not sure that it's correct to say if you have a box of 100 angstroms to set a maximum distance to 500 angstroms. I mean, it may be, maybe not. With periodic boundary conditions, it really depends on what you're doing.
At this point, using the SMD method itself that is already implemented by the 14 NAMD would be very effective. Because it's not computed the distance, it's just holding one point of your structure and pulling the other. So in your case.
Right, but what if you're pulling two molecules apart? The distance keeps growing, but the molecule comes back the other way and then run against each other.
Yeah. Come on, that's yes. You also have the same.
The SMD, the older SMD code has the option of just doing a constant velocity, but in the set direction, that's one option too. But I mean, this is if you apply a force to the distance, it's going to go towards larger distance in hopefully the lowest free energy pathway. So it's going to choose the direction. If you do want to not have periodic boundary conditions, you can actually tell the distance to be calculated ignoring PBCs. So let's say here that I'm doing also a gas-phase system, so PBCs aren't there, so ignoring them is not going to change, but let's do it. Okay? Yeah.
I remember I had before the SMD and NAMD, you need to choose, you need to select the force, the direction of force applied to the interest atom. So, can we define the the direction of force we apply here in this cobalt.
You are implicitly doing that because you are doing the distance between center of mass. So to increase, you only have one direction, right?
Well, it's going to pick one direction. Like if I push them to go, they could go this way or they could go this way. They will choose they will choose the most convenient pathway, which is always what you want, because you don't want to go the less convenient one. If you want to set the direction, it's possible to do that with another variable, but let's talk about it on the side. I'll run this input. Hopefully I don't have any typos. No. It's fine. One thing that I haven't done, but it may be good to do that, is so I can do the simulation like this. So I can redirect your file either with T or with the greater sign. So it runs the simulation here, but then it prints the .log file that I can look at. Okay, so this is the log file from NAMD. Now that I have more interesting things undefined, maybe we can take a look at the messages when Progress is initialized. So this is where you started from the first time, but initially you don't load any configuration, but it tells you the version number here. This is the version number for the Corvus module. So the library itself is being included in NAMD, VMD, and LAMS. So there's one version number there that changes continuously, and of course, one version of VMD or NAMD is going to have a precise number for this. So 2.12 has something that is from the last December. And this is the version for the NAMD interface. It's not terribly interesting. It's just different parts of the book. The real interesting stuff is here, so reading new configuration. So it's parsing, looking for different keywords, and each one keyword that is missing, it shows the default value. If the default value is good for you, you don't have to add it yourself. It just tells you what it's assuming. And generally, I try to maintain default values carried over between versions. So if there is some discontinuity, it's gonna raise an error or like be honored in the old one. So here's where you define the variable, and here's where you define there's a bunch of options for the atom selections. You don't need to read all of them. Just know that there's multiple ways how to define the atoms. This is one interesting thing. So this is looking at the NAMD Corvus interface. And this is the data for 0 atoms. Wow, we haven't used anything. It's actually because we have requested a variable that is defined on centers of mass. Sometimes centers of mass of whole groups. So actually, NAMD doesn't know what these atoms are. It just passes them to NAMD, and NAMD computes the centers of mass in parallel. So this is what it means. So there's 2 groups and 27 atoms in total. Yeah?
So what's the keyword analysis for? Analysis is for?
It's kind of old, and I'm probably going to remove soon because at some point you could do analysis on the fly, but now you can just load it in VMD.
Yeah, so I saw something like enable fit gradients on in the, like if you scroll up.
Yes. This is a more advanced feature
Yeah,
that we're going to talk about eventually, but not going into detail. You can define a frame of reference that has an orientation on a time-listed fit. And then when you take the fitting, you can define the rotated coordinates and define the variables inside the rotated coordinates. So now the variable depends on the atoms that you request, but also the atoms of the fit. So there's going to be some gradients on the outer of the field. That's what it is.
Yeah, if I may.
Yeah.
What Giacomo mentioned about the default values, NAMD follows this rule in every single keyword. So if you are not sure which value you are using, go check the manual, because NAMD will apply the default value, which might not interest you. Okay? Always check the default values that NAMD.
If the keyword is important for you,
Yes,
if
of
you
course.
don't care either way, leave
Just
the
leave
default.
it. It's better not to touch it.
And this is for the center of the restraint. So you can see here that we have tested 100,000 steps, and then we made the division by 2 using TCL syntax. It means that 50,000 was faster. So it actually read what we wanted. And then we just going to do calculations. So from time to time, I don't know how often does the restart get written here? Maybe not often enough, but basically we will print information just like NAMD does. Now we have results here. What we have here is, well, in this case, still the trajectory file in corrective variable space. Okay, now I have the step number R, the force applied on R, which you wanted. That's here. Then this is the center of the restraint, x0 underscore R. This is the restraint of the center of the restraint that is applied to R. So it starts at 0, and then it gets updated regularly because it's moving over time. And this is the accumulated work, so the free energy profile, so to speak. Now, you could plot this. For example, you could take this column and plot them along one another. And yeah, you can use GNU-plot, XMGrace, whatever. You have to remember which column this is. If you have a lot of variables and people are starting to use a lot of them, they can be tedious. So there's actually a script that will read the column for you. You will have to keep the name, and it will pick it out. And so that's the other folder. Okay. But it's also, this script is also available from the Corvus repository. You just bring it from there. Otherwise, you just count which column it is. I'm doing it here one per minute because I don't want to count. So let me check what does the file contain. So I take I run the script, and I give the argument list variables, and then I give the name of the trash file that's in there. If it's multiple ones, it's going to be more of them. So this variables tells us, without reading the whole thing, that there's 4 columns in the file. R, the force applied on R, the center of the restraint, and the work performed by the restraint. I call the restraint harmony, so this is work underscore harmony. Now what I can do is I can extract it, for example, I can tell it to read all the Corvus directory files and write to this file only variables that I select. So then you know that if you write this file, the columns are the ones that you want, and then you can plot them this way. And, okay. Yes, I forgot something here, because variables can be a list of things. So you don't want the script to think that the touch file is another variable. So you put a dash dash here. I'm done with this option. Okay. Then I can look at the SMT-work And now this is what I wanted. This is still the step number. It's going to be in there. You can't remove it. Maybe you can do some awk, up to you. But because you may define variables or biases during the simulation, after you started it, it's important to know to have this step number in there. You can remove it, of course, if you want. This is the center restraint. This is the work. And now I can plot. This will be the syntax we can plot, but really, it's up to you what you use to plot. Okay? So this is now on the x-axis, there's the center of the restraint, R0. On the y-axis is the work in the units of energy that NAMD uses, kcal per mole. So we start at 0, we go 0 down because actually the minimum is around 5, or looks like the minimum of the free energy should be around 5. Then it goes up again, and then it kind of settles. Maybe there's going to be another bit. Okay, also, you're eventually going to see the Jacobian term if you go to very long distances. The logarithm of r is going to come in so only later. So yeah. So that's how you can basically get the state and the work. The script itself also has some functions that use matplotlib. So you can basically do this. So you can say, you can, instead of writing to a file, you can write to a PDF file directly. You can say that the x-axis of the plot is going to be, instead of time or step, is going to be the center of the restraint. And then you can do this. Fine. If you don't specify the x-axis, this is going to be the plot, the summary. You can customize, if you're familiar with matplotlib, you can load the script and then customize the plot. Yep.
Sorry, I'm a little lost between R and R0.
R is the actual distance between the two groups.
Center of masses.
Center of mass.
And R0 is what you're trying to turn it into?
R0 is the minimum of the applied potential that I put in there all the time.
Oh, okay.
It's a spring potential, and the spring has a minimum at R0.
Right. So you're essentially making the string bigger and bigger.
Yeah. Making the minimum of the string and the minimum of the spring bigger. Yes. I think this is all I wanted to do for basic syntax. I would say now that you guys should start with the tutorials.